Hi, everyone. We're back, and we're getting into implicit differentiation. Here we've got the folium of Descartes. Super cool. We got a loopy thing. Um, this is not a function of x nor y. It's a relationship between the two things. And so we're going to use implicit differentiation to find slopes along this curve. Okay, so big idea with implicit differentiation. Let's go ahead and just copy down that original equation. X cubed plus y cubed equals 7xy. The idea here is to just take the derivative of everything with respect to x, and we're going to do that term by term across the entire equation. 3x squared, no big deal, our rule for that first part. Then remember, we're treating y as some unknown function of x, and so we're going to do a chain rule. Chain rule on this looks like 3y squared, but remember, as a last step in chain rule is we multiply by the derivative of the inside function. And so we could either write that as y prime or dy dx would both be good representations of the derivative. On the right-hand side, we've got 7xy. This is actually a product rule because we've got 7x as a function of x and then y as some unknown function of x. And so let's treat 7x as our first function and y as our second function. If I take the derivative of the first function and multiply it by the second, I would get 7y. And if I leave the first function alone and I multiply by the derivative of the second function, I would have 7x times y prime. And so that is the product rule on the right-hand side because we've got a product of two functions of x. Now we're at the stage where everything has already taken the derivative of it. Like the calculus, to some extent, is done. But in order to get it into a nice, form that we might be able to use, what's helpful is to solve for y prime or to solve for dy dx. And so let's go ahead and just move those so that we're taking everything to one side. Let's go ahead and leave 3y squared y prime on the left-hand side, and let's subtract 7x y prime. So that's coming from the right-hand side. We're doing this, and then we're doing this. And on the right-hand side, let's leave 7y alone. And then we're going to subtract 3x squared. That's fine. So I'm just, whoops, that's not where that goes. That goes down here, and this one goes all the way over, boom. So just rearranging these so that we can factor out y prime on the left-hand side. Using the distributive property, we've got y prime is 3y squared and then 7x, just chilling. Okay, and then solving for y prime looks like, and 7y minus 3x squared. Oh, that was a bad one. And then we've got 3y squared minus 7x on bottom. Cool. So that is a way to encapsulate the derivative dy dx. I might as well, write that. I've opted for the y prime notation just because it's more compact, but you could totally write dy dx everywhere where you see y prime. So we've got a derivative, but we want to utilize this result to find the coordinates of the rightmost point in the loop. Okay, so we want to find what are the coordinates of this point, and we're going to have to use some information about the derivative to do that. This rightmost point is going to happen where we have a vertical tangent line. a vertical tangent line is going to happen when the denominator of this fraction goes to 0. That's where it's going to look like we've got an infinite slope. So what we're going to do is we are going to bring this all the way up, and we're going to set the denominator equal to 0. 3y squared minus 7x equals 0. And, more friendly, that's going to be 3y squared equals 7x. Okay, cool. How are we going to utilize this to find that rightmost point? Well, this gives us another constraint. It gives us another relationship between x and y, where if we utilize this relationship in conjunction with the original equation we have, hopefully we'll be able to find some pair of x and y that satisfies both of these equations at the same time. So we're doing this a simultaneous set of equations. Probably the easiest way to solve this will be to use substitution. Let's go ahead and do one more step here. We'll divide both sides by 7 so that we've got 3/7 y squared equals x. Then I'm going to go ahead and make this substitution and plug it in to the original equation. So going from this original equation, we're going to substitute in 3/7 y squared in for x. And so we're going to cube that. Y cubed is just going to chill. And then we're going to have 7. We're going to replace x with 3/7 y squared. And then y is just going to chill. So that now we have an equation with just one unknown. And hopefully we're going to be able to solve for this. All right, well, so let's simplify things down. We've got 3/7 cubed. We've got y to the 6th. We've got y cubed and, 3y cubed over here. That's not so bad. Let's factor this a bit in order to get it nice. Let's go 3/7 cubed, y to the 6th. We're going to subtract 3y cubed from both sides, so we get a minus 2y cubed over here equals 0. Then another step could be factoring out x or y cubed, so that we've got 3/7 cubed y cubed minus 2 equals 0. So we just pulled out that common factor of y cubed from both of those terms. Whew. And so now, by using the zero product property, this is either y equals 0 would be a solution to this entire equation, or all of this equals 0. 3/7 cubed y cubed minus 2 equals 0. And so we can solve for y here. Let's make this up and just keep writing small. We can add 2 to both sides. And then we can multiply both sides by 7/3 cubed. And then we can take the cube root of each side. So we get y is equal to 7/3 times the cube root of 2. And that is actually a nice, important point. That tells us the y value of this point over here. Gross. The y value of this point over here is 7/3 cube root of 2. Um, Notice that there, at y equals 0, there was another option for having a vertical tangent line, but we don't want to focus in on that one. We want to focus in on this one. And then if we wanted to find an x value associated with that, we could plug in that y value, back into here. Probably be the nicest place to go, but we would also get, a ridiculous looking x value. So I kind of don't want to compute it right now. But yeah, if you plug this back into this equation or this equation, and you can get an x value without too much trouble. This is already very full screen. Let's go ahead and take a look at what this looks like on GeoGebra. All right. Well, that looks like a folium. All right, so the blue curve is the original folium. In GeoGebra, one thing that I've done here is I have made a function little m, and it has two input variables. So technically, this is a multivariable function. What this is supposed to represent is the implicit derivative that we found earlier. Um, and so, we found this. Notice that if I type this in as a function, there is no graph that shows up because we've got a two-dimensional input, we've got two input variables, and then we'll have something as an output. We would need 3 dimensions in order to graph this entire thing, input and output together. So we're going to save graphing this type of thing for Calc 3. But GeoGebra can still recognize that this is a function, and if I utilize it in other functions, it can calculate things based on x and y values that I put into it. So that's how I'm getting this thing to drag around and keep the slope going. But yeah, what we found was the point that y value was 7/3 times the cube root of 2, and it looks like the x value is still just 7/3 times the cube root of 2 squared. Um, yeah, we saw that squared thing probably coming about when, if we threw it in here, that would pop up. Um, cool. So we found the coordinates of the rightmost point in the loop. And, because we were able to express our derivative in a general form, we could find the slope at any point along that curve that you want. I mean, notice that when we get to the point 0, 0, it freaks out and doesn't know what to do because, technically there's a vertical tangent line there. There's also a horizontal tangent line there too. Depends on which portion you're kind of concerned with. So it gets a little hairy there, but things are good. We've, conquered an entirely new set of scenarios and we can find derivatives. Cool. All right. Let's keep going. Here we've got another weird looking curve. Here we're trying to determine the derivative and use it to find the equation of a line that's perpendicular at the point 3, 2 and a point that is normal at the point 3, 2. So it has, it's perpendicular to the tangent line. Cool. At what point does the curve have horizontal tangents as well? Okay, so that one's later. Let's try to do this one. All right, so we're starting off. Let's go ahead and just copy down that entire equation. 3 minus y cubed plus y squared plus 5y minus x squared equals 0. Flip. Okay. We are going to take the derivative of everything with respect to x. So when we take the derivative of 3, we get 0. When we take the derivative of negative y cubed, we get negative 3y squared and then times y prime, or dy dx. Let's go ahead and write dy dx this time. We haven't done that yet. Okay. For the next one, we're going to have 2y and then dy dx according to the chain rule. For the next one, we're going to have 5 times dy dx according to the chain rule, because again, y is some unknown function of x. And then minus 2x power rule, and then equals 0, again, derivative of 0 is 0. So cool. We now have taken the derivative of everything, and one of the cool things about this is that we can kind of take a shortcut at this point. We could do the work of getting 2x on the right hand side and then dividing out a dy dx from everything and making this a like a rational function is what you would end up being if you solve for dy dx. We totally could do that. But since we've already done the calculus and we already know that there's a point that we are interested in, one of the things that you can do to save yourself some time is just to start plugging in those values for the point right now. And so if we went -3 with a 2 squared instead of y squared, and then 2 times 2 dy dx, and 5 times dy dx, and minus 2 times 3 for the x coordinate. Sometimes this will save you a lot of time. Sometimes maybe not as much. I feel like this is kind of in the middle. What's nice is, now we've just got a bunch of numbers that simplify down. So 2 squared and then times -3 gives us -12 dy dx. Oh, geez. Then we've got a +4 dy dx. And then we've got a +5 dy dx. And then a -6. And so we can solve for dy dx maybe easier now. If we combine the like terms here, we've got +9 but -12, so that's a -3 dy dx. And I can add 6 to both sides. And so dy dx should be -2 if we, divide -6, or sorry, divide 6 by -3. -2, that's better. And so, I don't know, maybe plugging those numbers in early helps us find that. I'm going to go ahead and move this over a bit. Let's go right there so that we have some more room to the right. And so, yeah, that's telling us that the slope of our tangent line should be -2 at that point. And if we wanted to find that red tangent line, no, oh, it's okay, it's okay. If we wanted to find that red tangent line, we could use that slope of -2 and go y minus the y value, which is 2, equals m, which is -2, times x minus the x value, which is 3. And so, if we shake this out, -2x plus 6, y equals -2x plus 8. Let's go ahead and go to GeoGebra and make sure that that's right. There, I've got that function again. Okay, boom. Y equals -2x plus 8. That one looks good as a tangent line. So far, so good. For our normal line, we'd do the same thing, except we would use a perpendicular slope. Remember, that's an opposite reciprocal. So it's still y minus 2, but then we've got a slope of 1/2, x minus 3. And so this should be y equals 1/2 x. And then we've got a minus 3/2 plus 2. So it should be a plus 1/2. And so that's our green normal line. Cool. Oh, and if we wanted to find at what points does the curve have horizontal tangents, oh, this is where it's coming back to bite me. That we didn't solve for dy dx. I did earlier, and then I decided not to right now. Let's look at this. All right, so if we did solve for dy dx, we'd have 2x minus 3y squared plus 2y plus 5. And that would just be working with this equation and simplifying it down so that we've solved for dy dx. So yeah, that makes sense. So let's go ahead and write that real quick. dy dx. We add the 2x over. It should have a 2x there. And then we're going to have a negative 3y squared plus 2y plus 5 in the denominator. I think that's a good, simplified derivative. But yeah, what we would want to do is set this equal to 0. Set that derivative equal to 0 so that we can find a horizontal tangent. And if we're setting that whole thing equal to 0, let's use purple. Really, that equates to just putting the top equal to 0 while the bottom isn't equal to 0 at the same time. And so x equals 0 is a good x-coordinate where we'll have a horizontal tangent. And then if we were trying to find the spot where it actually does have a horizontal tangent, we want to find not only where x is equal to 0, but we want to find the specific spot where this has a flat slope. So we would have to go back here, and if we put in x equals 0, we would have a cubic equation in y, and how that cubic equation would solve out to be would have 2 roots. Oh gosh, that here, I'll go ahead and write it. This is not something that I'm going to ask you to do too much of. So I'm getting a little bit lazy here. But if we plug in x equals 0, 5y, all right, x squared is there no longer. This is a cubic equation in y, and the way that this should shake out is to have, if we factored it, it would have y plus 1 squared times y minus 3. And I'm not going to ask you to factor cubic equations. There is a cubic formula. This is, kind of crazy. But the point where this actually has a 0 slope is where the top function is 0, but the bottom function isn't 0 at the same time. So I guess, okay, this was fine doing that, and we found all the roots, but it actually would be even better if, let's use light green. If we set this equal to 0, the denominator, then this would give us points to avoid. because we wouldn't want to have an indeterminate form. So if we set that equal to 0, we would be able to factor that into a couple of things. Now, this is a quadratic. Can I do this? I should be able to do this. Negative 3y and a y. We need a 5 and a 1, and we need the middle to come out to 2. So we want to do 5 times 1. Okay, so plus 5, and then we want a plus 1 here. Okay, so I think that that works out. No, it doesn't. Negative 3y squared. And then we've got a minus 3y and a plus 5y. That gives us the plus 2y. The factoring's okay, but what does that even mean? Y is equal to negative 1 and y is equal to 5/3? Gross. What does that mean? I was hoping that this would be better, but it does. Okay. So at those places, we would have vertical tangent lines. Oh, yeah. Y equals 5/3. Okay, so that's a point where we have vertical tangent lines. And then y equals negative 1 is a spot that we would also want to avoid. So I guess with these two things in conjunction, what we would be able to say is that at y equals negative 1, we have the numerator of this fraction equals 0, but also the denominator of this fraction equals 0. And so it's an indeterminate form. We could talk about indeterminate forms and, calculating the slope there at some other point. Um, but what that information would tell us is that we should ignore y equals negative 1, but we should utilize y equals 3 as our horizontal tangent line. So that one's the one that we're going to go for. Okay, that's crazy. I don't want to stay too long here. The big idea is the new implicit differentiation thing. We were able to get a lot done on this curve. That's what we're looking for. Gosh, the next one. Okay. Here we're gonna do two derivatives real quick. So we got the unit circle. Let's do implicit differentiation twice. And yeah, hopefully this will be good. All right. Let's start here. X squared plus y squared equals 1. Take the derivative of everything with respect to x. We get 2x plus 2y y prime equals 0. So we needed to do a chain rule on the y squared part, but that is maybe starting to become second nature. At this stage, we could subtract 2x from both sides and then divide by 2y so that we get negative x over y as our first derivative. So that's pretty cool. Then what we would want to do to get our second derivative is take the derivative of both sides, again, implicitly. So if we take the derivative of y prime with respect to y, we get y double prime. And that's it. Remember that we could write y prime as dy dx. What we're doing when we take the derivative on both sides with respect to x again is we are doing this. We're doing d dx of dy dx. And so we get this weird notation of d squared y over dx squared, which is the second derivative that we're looking for up here. So I want you to notice that in the background that this is the definition of y double prime. And so there isn't chain rule craziness that needs to happen on the left-hand side. That's already taken care of just by taking the derivative. It just becomes y double prime. On the right-hand side, however, there will be a quotient rule. We've got this negative x over y. There's a quotient rule that needs to happen. Let's go ahead and just bring that negative along and not even deal with that anymore. Now we're treating the top as x, the bottom as y. Let's do low d high. So the bottom times the derivative of the top. So y times the derivative of the top is 1 minus high d low. So x times the derivative of the bottom, that one will be y prime, all over the bottom squared. So that'll be y squared. And the cool part here is that we can solve for y double prime, especially if we substitute in for y prime, x times y prime was negative x over y. So now if we reduce this mess, we should have something that ends up looking pretty nice, I think. So we've got y minus, plus x squared over y, and then y squared. So let's, let's divide by y squared, both of those terms. We would have negative 1 over y minus x squared over y cubed. All right. That feels okay. Give me a second. Okay. So I just went and I checked in the book because I remembered that the answer in the book looked a little bit different, but our answer is fine. Here, I'll go ahead and I'll paste this in and we can just compare it real quick. I remembered that in the book, it was like only dependent on y, and that was pretty cool. What they did was they made a clever use of the original equation to make it look like this. So at this stage, we are, completely the same. I know, yeah, this negative sign is applying to, the entire or the entire fraction. So if we multiplied the numerator by -1, we would have the same thing. But the idea being they multiplied the numerator and denominator by y so that they got negative y squared minus x squared on top. And then they were able to utilize this relationship, which was the original unit circle, to turn this into a -1 instead of negative y squared minus x squared. So they ended up with, -1 over y cubed, which honestly, that's a little bit more elegant than what I wrote here, but it's not wrong. Yeah, we could work with this too. That's totally the same thing. Um, but anyways, yeah, we were able to find a second derivative there, which is cool. More practice with implicit differentiation. the last section here is on derivatives of inverse functions. And this is, it's interesting, it's cool. It's one of those things that's going to show up in homework, probably going to show up on activity. Um, may or may not show up on tests. This is not the kind of thing that I necessarily want you to have to memorize. Let's take a look at what we've got going on here. In this original picture, we've got f as the blue function and then f inverse as the red one. Remember that inverse functions have this nice symmetry over the line y equals x. And for any point c, f of c, on the original function, the point f of c, c is going to be on the inverse function. So you just exchange the roles of x and y. Super cool. If we go down here and we take the derivative of the composition of a function and its inverse in two different ways, we're going to use implicit differentiation here. So here, the original function's on the inside. Here, the original function's on the outside. When we do implicit differentiation, we're going to be utilizing the chain rule both times. So the chain rule here, you're taking the derivative of the outside function, leaving the inside function the same, and then you're multiplying by the derivative of the inside function. Again, chain rule, you're taking the derivative of the outside function, leaving the inside function the same, and then multiplying by the derivative of the inside function. Working these out in both ways allows us to get formulas for either one of these scenarios. So if we wanted to find the derivative of f inverse, this is a nice formula. The blue one is probably the one that's more useful. So yeah, if we have an inverse function and we want to find the derivative of it real quick, we can do 1 over the derivative of the outside, so derivative of f, with the inverse function composed on the inside. This one is the derivative of the inverse function with the original function composed on the inside is equal to 1 over the derivative of f. That's just kind of a cool relationship between the reciprocal of the derivative of f and the derivative of the inverse function. And if you stare at this picture and look at these relationships, you can see that those slopes end up working out. Here, if we've got a slope of m, the slope on the inverse function ends up being 1 over m, and these kind of things work out pretty nicely. We totally could do example 1 here and plug things in the right spot. Yeah, I will say though that this is something that I don't want you to have to memorize. So let's do it, and I'll try not to take too much time doing it. All right. So here we have the function x squared, and we're going to try to determine the derivative of the inverse function when we're plugging in 4. So if we just go and we utilize, I don't know, let's go a over here, right? That right-hand one, we've got the derivative of f inverse. We're going to do 1 over f inverse, or sorry, derivative of f, f inverse of 4. So, on this one, f inverse of 4 would be like the square root of 4. Since f is the squared function, f inverse would be the square root function. Why is this not appearing? Great. Uh, Hold on one second. This isn't writing. I'll be right back. Okay, we've got this figured out. I'm sorry that this wasn't showing up earlier. Um, so the idea is we're utilizing this blue formula here, and we are plugging in 4 in for x. We've still got f prime there. Um, f inverse is square root. And so we've got 1 over f prime of 2 as the thing that we're actually working towards. I think we can fit in one more line. F prime in this case would be, you know, 2x. By the power rule. And so this is 1 over 2 times 2, or 1 over 4. Goodness. Um, if we went to GeoGebra real quick to graph this up, I don't think I have this already done. Let's do this. Let's do this. Sure, leave. Um, f of x was x squared. Nope. Please. Thank you. Okay. Um, there's our original f. Um, we were also interested in f inverse. Let's do like that. Um, we know that it is, the square root function. And if we really wanted x squared to have an inverse function, remember that we would have to restrict its domain. So if I went up here, if I said x greater than 0, oh, nice. Okay. That's going to restrict our domain so that we do have a purely nice inverse function here. The idea was in this problem is they were asking us to find the derivative of the inverse function at 4. So, you know, at the point 4, f inverse of 4, nope, I said 4, but I typed f. Oh, please. Oh, wait, f in, boom. Okay, we're at the point 4, 2. The number that we found out was 1/4. So the idea being, if we created a line here that, oh, lovely. I'll have to do this the old-fashioned way. Y minus 2 equals the slope of 1/4 that we found times x minus 4. Boom. That gives us a tangent line for the inverse function. This doesn't feel like super useful to me. I don't know. But we were able to find that slope of 1/4 earlier, um, by utilizing, this combination of things. I guess we wouldn't even really had to know that the square root function is the inverse function. Technically, we could have just thought about what input gets mapped to an output of 4, and then realized that an output of 4 goes back to 2 as an input. So maybe technically we could have done this without the square root function and actually having to label the inverse. But anyways, yay, we can calculate the slope on the inverse function when we're, given that. And goodness, we could do this one too. It's just plugging things in. I feel like I'm already long. So let's go on to the other stuff. It's more important. Um, Here's taking the derivative of the natural log of x. And similarly, finding the derivative of any log base a. So, um, yeah, remember last time we calculated this kind of derivative using the chain rule um, for the exponential function. We were up here, and we did this natural log of 2 thing for 2 to the x. That was fun. Um, Then coming back down here, this is a similar scenario. If we've got y is equal to the ln of x, the relationship between all of those variables is e to the y is equal to x. That's another way of rewriting things. You can, think of just exponentiating on both sides. But if you take the derivative of this part implicitly, we get this as a derivative. We solve for y prime, we get 1 over e to the y. E to the y is equal to x. So the derivative of the natural log is 1 over x. And similarly, if we throw in a factor of 1 over the natural log of a, that comes in via the chain rule on this one. I guess for example 2 here, I circled A because it's actually a little bit interesting. The other ones, they're not that bad. It's just applying the formulas that we saw earlier. But if we take the derivative of y equals ln of kx, where k is just a positive real number, you'll notice that things cancel out nicely using the chain rule. So, you know, here, if we've got dy dx on that left-hand side, we take the derivative here, take the derivative of the outside is probably the move first. Uh, so derivative of the outside function is 1 over the inside. And then we multiply by the derivative of the inside, that's k. And so the derivative of ln of kx is just equal to 1 over x. It's the same exact thing as just the normal ln of x. So putting any positive real number in here gives you the same exact derivative. Reason being is that we totally could have used properties of logs to write this as ln of k plus ln of x, separating that multiplication inside the argument into addition. And if we look at it this way, really ln of kx is just a vertically shifted version of ln of x. So it makes sense that the slopes should be the same. I don't know. It's kind of cool. Okay. Last major technique thing, we're going to look at logarithmic differentiation. This is helpful when you see a whole bunch of powers in what you're taking the derivative of. Properties of logarithms are nice because they can take powers and turn them into multiplication, or they can turn multiplication on the inside of an argument into addition on the outside. They can make things simpler in certain cases. And so whenever we see something that has a lot of powers in it, especially a power function, an exponential function that looks like x to the x, we don't have any tools for taking the derivative of this kind of function yet. So what we're going to do is logarithmic differentiation. I might leave this up there so that, you can read it as we go along. But I think I've got enough room on the right-hand side here to kind of squeeze things in. We're going to do part C. The other two, parts A and part B here, those ones that you could do without logarithmic differentiation, it would just be a colossal pain to do the quotient rule and chain rule and this kind of stuff, and quotient rule and product rule and chain rule on this kind of stuff. It would be gross to do it in this kind of a form, but technically it would be possible. In part C, though, this is a new type of function that we would not be able to tackle without logarithmic differentiation. And so I feel like it's more important to look at this one. Okay, idea being, let's just write this as y equals 2, sorry, x to the 2x. Then we're going to apply the natural log to both sides. Natural log of y equals the natural log of x to the 2x. Cool property of natural logarithm is that exponentiation that we see inside the argument can be turned into multiplication outside. So on the left-hand side, we still have natural log of y, but on this side, we could have 2x times the natural log of x, bringing that exponent out front. Notice that we haven't taken any derivatives yet. This is just rearranging the original equation that we were given. We're using properties of logs. Now is when we will do, I guess this is step one. Step two comes in here where we take the derivative of both sides, assuming that y is differentiable. On the left-hand side, if we've got the natural log of y, and we're taking the derivative with respect to x, what we'll get is 1 over y as the derivative of the outside function, but the derivative of the inside function would be dy dx. So that's taking it implicitly on the left-hand side. On the right-hand side, we've got a product rule. So we would have 2 ln of x plus 2x times 1 over x as a product rule there. And then we could solve for, y prime or dy dx. We could multiply both sides by y. And so bringing y over to the right-hand side, remember that y is equal to x to the 2x. So I'm going to maybe take a tiny shortcut here. I'm going to rewrite y as x to the 2x power, and that's times all of the result of this product rule. And so there we found the derivative of x to the 2x using logarithmic differentiation, and it's a derivative that we would not have been able to get otherwise. So that's pretty cool. And real quick, I've got this on GeoGebra. X to the 2x is a real weird function. It has this kind of a shape. But yes, the derivative is indeed what we found. And, just for fun, if we wanted to find the slope of the function at x equals 1, we could find a tangent line there. We could utilize this derivative that we calculated, plug in 1, and yeah, get a nice tangent line. So this green function is a new type of function that we've conquered in our search for taking the derivative of everything. Cool. Um, Last major thing, and I promise that this is the last thing. I don't even think we're going to do any of these. Let me just explain where these inverse trig derivatives come from. There's 6, and these are things that, again, I'm not going to have you memorize. These are things that you can totally just like look up in a table and utilize. Once you're used to doing derivatives, having some extra derivative formulas is not that huge of a deal. The idea being, um, is that we could derive these, but it's it's too much for my mind to remember the intricacies of these long term. It's easier to kind of derive them individually. Let's say we were going to try to derive the derivative of the arc sine. We're working with the inverse sine, arc sine, and we want to calculate the derivative. Here, we're utilizing this, blue formula that we had earlier, um, up right here. And so, what we're utilizing is, oh, hey, if I want to calculate the derivative of the arc sine, that is 1 over the cosine of the arc sine of x. And this is one way to write that, but it's, maybe not super satisfying. This probably could be combined and reduced into a simplified form. The idea, I don't know if you remember doing this in like a pre-calc class, but when you've got an arc sine and then you've got a cosine around it, for instance, whenever you've got a composition of an inverse trig function and a regular trig function, this can happen in the opposite order too. It's oftentimes really nice to draw a triangle to sort out your thoughts. And the idea being, this arc sine of x asks the question, where, for what angle theta would the sine be x? And so if we draw a triangle where the sine, or the ratio of the opposite side to the hypotenuse, is x, here x is that side, the hypotenuse is 1, so that the sine of theta equals x. One thing that we can do is utilize the Pythagorean theorem to find the length of that other side. Then we have a right triangle that works nicely with the Pythagorean theorem, and we've got our angle theta there. And so the idea being that the arc sine of x is this angle theta, and then if we say, I want to find the cosine of theta, the cosine is the adjacent over the hypotenuse. And so if we continue to follow this, the denominator of this fraction ends up being the square root of 1 minus x squared. And so this being the derivative of the arc sine is, how we might derive that using this inverse derivative formula. I know that that's maybe not like a super exciting place to end this on, but I think that I probably kept you long enough. Um, we totally could use these in conjunction with the chain rule and just utilize those. If we need to do that, I'll be happy to help you. Um, if this ends up coming up on the activity or the homework. Um, thank you for working through this with me. I hope that you have a good day, and I will see you tomorrow when we have an activity. All right, see you then. Let's